Hi everyone, welcome to 9.5 Inequalities in Two Variables. Today we're going to be graphing linear inequalities and nonlinear inequalities. So this will be a good review on all types of graphs that we've done thus far, just we're adding the component of inequality to it. So to get started, a solution set of an inequality. A solution set of an inequality in two variables is the set of all ordered pairs with real coordinates that satisfy the inequality. The graph of the inequality is the graph of the solution set. So basically we're thinking shaded region, okay? So the extra thing we have to do today when we're graphing these inequalities is we have to think about, is our boundary dashed or solid, where are we going to shade? Where is the solution to this inequality? So let's go ahead and get started with our first example, focusing on linear inequalities. So what we can do first is recognize that if this were an equation, this would be in standard form. So when we're graphing a line in standard form, all that I require you to do is state the intercepts. Plot the intercepts, draw our boundary, and then we'll go from there. So our x-intercept, so when y is equal to 0, we get x to be 3. And when x equals 0, we get y to be -2. So those are our intercepts, okay, our x-intercept and our y-intercept. All we have to do is plot those points. So let's go ahead and plot those points. 0, -2, 3, 0. And now one thing we have to keep in mind is because our inequality is less than, that means we're going to have a dashed boundary. Hopefully we remember that. Okay, so strictly less than or strictly greater than tells us we have a dashed boundary. So we can go ahead, connect these guys with a dashed line. And now the last thing we have to figure out is where are we going to shade? So we need to check a point that is not on our boundary. So I like to check 0, 0. All right, it's a nice simple point. All right, so we're going to check in the original inequality. Okay, so when x equals 0, we can plug in 2 times 0 minus 3 times 0, and we're checking to see that it is less than 6. So the left side all goes to 0. And we get an inequality that says 0 is less than 6. If that's true, which it is, that means we're going to shade in the direction of that point. Okay, so since that's true, we're going to shade over on this side of the line. Okay, and a solution to the system is any ordered pair in that shaded region. Okay. Okay, so now let's go ahead to the next example. All right, y is greater than or equal to -3x plus 7. So what we should recognize here is that this is in slope-intercept form. So our y-intercept is 0, 7, and our slope is -3. So we'll use that point 0, -7, and our slope of -3. All right, so 0, -7, we plot that, and then I'll use that slope of -3 to get some more points. So down 3 over 1, down 3 over 1, all right? And now we need to double check, is this going to be a dashed or solid boundary? And since it's greater than or equal to, now I know it's going to be a solid boundary, which is different from the previous example. So we can go ahead and draw our solid line straight through those points. Okay. And now again, we still need to check a point. Since 0, 0 is not on my boundary, I can go ahead and check that. And if you need to go ahead and write the side note of the check. So when y is 0, is that greater than or equal to -3 times 0 plus 7? And we end up 0 greater than or equal to 7, which is not true. Okay, so what does that mean? Where are we going to shade? We are now going to shade on the other side of the line. Okay, so any ordered pair in that shaded region is a solution to our inequality. We will now move on to non-linear inequalities. So this will be a good review of graphing quadratics, only now we're throwing in the inequality aspect along with circles, exponentials, and log functions. So this first guy here in example A, y is less than or equal to x squared plus 2x minus 3. Hopefully we recognize that this is a quadratic. So what we need to recognize also is that we'll have a vertex. So remember, when we're in this standard form, our vertex, we have x is equal to the opposite of b over 2a. Okay, and then to find the y value of our vertex, we'll simply plug that x value back in. So let's see, our b value will have negative 2 over 2 times our a value, which is 1. So what we should get here is negative 1 for the x value. And when we plug that back into our, pretend it's an equation, when we plug negative 1 back in for x, we will get y to be negative 4. I apologize for the noises on my phone. So there is our vertex. Now we can create a table of values, putting that vertex right in the middle. Okay, and I'll pick some values that surround it, just because we know we're symmetric. All right, nice easy point. When x is 0, we should get negative 3 for y. And since this is a symmetric graph, when x is negative 2, we'll also get negative 3 for y. When we plug 1 into our inequality, we'll get y to be 0, and same goes for when we plug negative 3 in. So now we can go ahead and plot these points. As we're plotting, we should be thinking if our parabola is a solid or dashed curve, and we should note that since it's less than or equal to, we've got a solid curve going on here. So let's go ahead and plot these points. We've got negative 1, negative 4. We've got 0, negative 3, negative 2, negative 3, negative 3, 0, and 1, 0. So we can go ahead and connect these as best we can. And now we still need to test a point. So since our origin 0, 0 is not in or on our curve, we can still check that. So again, if we check the left side, y is 0. Is that less than or equal to? Well, when I plug 0 in for x, that goes to 0. This goes to 0. I'm left with 0 is less than or equal to negative 3, which is false. So where are we going to shade? Well, that point is inside of our curve, right? So since it's false inside, we're going to shade to the outside, like so. Okay. Moving on to our next example. Does anybody recognize what that represents? Hopefully we can see that it is a circle. Okay, so we have ourselves a circle. And can we identify the center? Remember, it's that HK value. Our center is negative 1, 2, and our radius is the square root of that guy, which is 3. Okay, so we have a center of negative 1, 2, a radius of 3. Keep in mind, when we are going to be graphing, our circle is going to be dashed because we're strictly greater than here. So when we plot a circle, if you remember, we start by our center, negative 1, 2, and we use that radius to count 3 in up, down, left, and right directions. So from my center to the right 3, I'm at 2, 2. From my center up 3, I'm at negative 1, 5. From my center left 3, I'm at negative 4, 2. And from my center down 3, I'm at negative 1, negative 1. And now to plot or to graph this, we have a dashed circle through these points. Okay. And now again, we have to test a point. Now, the best point to test in a circle is the center. Okay. And the reason we like to test the center is because it makes this whole side go to 0. Okay. So when we plug -1 in for x at that point, we get 0 squared. So we get 0 plus, when we plug 2 in for y minus 2 squared, well, that's 0 again. Is that greater than 9? So we end up with 0 greater than 9, which is false. So if it's false on the inside, where are we going to shade? We're going to shade outside of our circle. So there we have a circle. Okay. Let's move on now to, oops, I forgot to lock this page. It's all right. Exponentials. Okay. So remember with exponentials, we create a table of values. So we've got x, we've got y. I choose the x value here. That makes our power equal to 0. So I'll put -2 in for x, and then I choose values that surround it. So -1, 0, -3, -4, just to get a good look to my graph. So when x is -2, we get y to be 1. When x is -1, we get 3 to the first power, which is 3. When x is 0, we get 3 squared, which is 9. When x is -3, we get 3 to the -1, which is 1/3. And when x is -4, we get 3 to the -2, which is 1/9. So as we can see, our y values are getting closer and closer to 0. So remember, that means we have an asymptote at y equals 0. So let's go ahead and plot that aspect in first before we get to the points, and then we'll have to think about shading as well. Okay. So if we plot our points, we're at -2, 1. We're at -1, 3, 0, 9. It puts us up there. We do have a solid curve to this, so we can go ahead and connect these guys with a solid curve. And now we have to think about shading. Okay. All right. So we want to pick a value that's going to make it easy to check. Okay. So it can't be on our curve. All right. And I want to choose a nice easy value. So I might choose something that makes y 0. Maybe I just choose the point 0, 1, because those are nice easy numbers to see if we have a true or false statement. So as we go through, I have, let's see. Oh, I'm sorry, that's not y 0, that's x is 0. So let's go ahead and test that. 1 is greater than or equal to 3 squared. We get 1 is greater than or equal to 9, which is false. So if it's false on the outside, where does that say we're going to shade? We will shade on the inside there. Okay, so as the curve keeps going, we're all in here. Okay. All right, so then finally, that's going to get us to our very last example. I'm going to try to move over here without being so shaky. I'm going to change something on this right away, actually. So I want to make this a greater than. All right, so let's make it greater than. Y is greater than log base 2 of x. All right, so now remember, when graphing log functions, we need to first convert it to exponential form. So this is a good reminder how to do that, okay? And we'll worry about the inequality when we're graphing and shading, okay? So step number 1, let's change this to exponential. Remember, we start with our base, We raise it to the other side. We set it equal to the argument. So we get 2 to the y equals x. All right, and now we can create our table of values. And we do it the same way, except now we're going to plug in for y instead of x. So I choose a value of y that makes the power 0, and I choose values that surround it. So 1, 2, -1, -2. When y is 0, we get x to be 1. When y is 1, we get x to be 2. When y is 2, we get x to be 4. When y is -1, we get x to be 1/2. And when y is -2, we get x to be 1/4. All right, now what about our asymptote this time? Our asymptote with log functions is a vertical line. All right, and what we should notice is x is getting closer and closer to 0 as y goes more and more negative. So we have a vertical asymptote this time of x equals 0. So let's go ahead and plot that first before we draw or plot the other points. All right, and now we can go ahead and plot the points, only this time note our curve is going to be dashed since it's strictly greater than. Okay, so let's go ahead and plot those points there. So we have 1, 0, we have 2, 1, we have 4, 2, and we're going to dash this. Okay. All right, so now we need to test a point. Okay, so pick a point that might be easy to test that is not on our curve. Okay, and we can go ahead and let's just test the point 2, 0. Okay, so when we have the inequality, we're looking at 0 is greater than log base 2 of 2. Well, log base 2 of 2 we should recognize is just 1. So we have 0 is greater than 1. Again, it's false. Okay, so we're not going to shade on the inside. What we're going to do is we're going to shade on the outside. But keep in mind, we have that asymptote there. So we cannot cross this asymptote. We're going to be outside of our curve, but to the right of that asymptote. So you have to be very careful and take that asymptote into effect when we're talking about our solution set. Okay, if that makes sense. All right, if you have any questions, we will meet at some point to discuss this. In the meantime, go ahead, get started on day 7 homework. Good luck. Bye-bye.